Understanding Physics, this is for Assessed Practical 12, which is investigating the inverse square law for gamma radiation. So what is the inverse square law? So if you imagine you had a source of radiation, so this is a light bulb giving off light, and as the light moves away from the bulb, the intensity is the amount of radiation per unit area. Well, if you imagine the radiation is filling up a sphere, then that sphere is getting bigger and bigger, so the intensity will be getting less and less as you move away from the bulb. That's pretty obvious, isn't it? Now, the surface area of a sphere is proportional to its radius squared. Therefore, the area will be getting bigger and bigger by a factor of x squared. So the intensity, which is the amount of radiation per unit area, will vary with 1 over x squared. And that is what we mean by an inverse square law. Basically, if x doubles, then the intensity will be a quarter. If x increases by a factor of 3, then the intensity will be decreased by a factor of 9. It follows an inverse square law. The intensity is proportional to x squared. And that should be the case for our gamma source. I mean, gamma radiation, it's an electromagnetic wave as well, and it will spread out. Imagine you're shining a torch, and as the distance from the source doubles, then the intensity will be a quarter, because the radiation will be spreading out over 4 times the area. Now, this is the equipment. You'll need a gamma source, and they're called cup sources, and they come in these little lead-lined boxes. You'll need a counter, which is this machine, top right, some kind of a detector. This is an electronic one, or you may use a GM tube, a Geiger-Müller tube. You'll need a ruler, and you'll need a stop clock. Hopefully, you will get to do this experiment yourself. It's always tricky, I know, for teachers. Maybe the teacher will demonstrate it and then you'll take readings and blah blah blah. Is that ideal? No, you are supposed to do it yourselves, but it's difficult for some departments to enable students to do it. But hopefully you'll do it yourself. Okay, or at least see it being done, and then you take the readings and then process the data. Safety, radioactive sources should be stored in a secure location. They should be in a safe somewhere locked away in the prep room. You always handle them with tweezers, yes. Never point the source towards yourself or anyone else. When you finish the experiment, wash your hands in case any radioactive dust has got onto your fingers or whatever. Basically common sense, and it's all to do with minimizing your exposure. And if you do that, you should be perfectly safe. Are you being exposed to more radiation than the common person who doesn't do A-level physics? Yes, but a tiny bit more. The risk is acceptable. So how do you do it? The first thing you should do is take a reading of the background radiation, the background count. So with nowhere near any kind of a source, just leave the GM tube and the counter running for a minute, and you should get about 10 counts per minute is average. And then you take that away from all of your other readings. And so you get what we call the corrected count rate for all of your other readings. Then I would suggest put your source in some kind of a holder. I actually, the box that the source comes in, I use that as a holder, and it's nice and snug, and you can move it backwards and forwards and change the distance. From 5 centimeters to about 30 centimeters, more than 30 centimeters, you'll find that the radiation has probably spread out a bit too much for you to get any kind of a meaningful reading. But I would say from 5 to 30, maybe 5 centimeters at a time, measure the number of counts in 1 minute. So it's counts per minute that we are measuring. Again, never point the source towards anybody. After a minute, you can zero the counter. Yes, so you're taking a reading, start your stopwatch, zero the counter. Well, actually, zero the counter, start the stopwatch, time it for 1 minute, counts per minute. Then you plot a graph of the corrected count rate against 1 over x squared. And if you get a straight line, that will confirm the inverse square law. Yes. Radioactive decay is a random process, so lots and lots of uncertainty, particularly for the bigger distances, okay, where it's spread out so much. I mean, if you had a very, very, very active source, then you'd get a better straight line, but then it wouldn't be very safe, would it? Yes. So anyway, you should get something that looks like a straight line. These are the bits we're going to tick off, pretty straightforward, and you'll see that L at the bottom there. This is our only opportunity to get that one, so make sure you do this. You must be able to tick that one off.